Hello everyone. Today we're going to be presenting our work on the kaggle competition Plant Seedling Classification for our CZ4041 project. So the agenda for today's meeting is going to be that we're first going to look at the problem statement for this competition, and then we're going to look at the exploratory data analysis and the data processing pre-processing steps that we performed. After which we will discuss the solutions trialed and implemented, our final leaderboard ranking, and a solution novelty. So the problem statement for this challenge is pretty straightforward. The challenge tries to test the accuracy with which species of a plant can be identified given the RGB image of its seedling. To accomplish this goal, we started off by trying to understand what the dataset actually looks like to decide how to model our approach to this challenge. So the first important step in this process was exploratory data analysis. So now we're going to take a look at the structure of the dataset. It contains images of around 960 unique plants taken at various growth stages belonging to 12 different species. There are 4,750 annotated RGB plant images available in the training set, which we then split by an 80-20 percentage for training and validation, and another 794 unlabeled RGB images in the test set. The images have variable sizes even within the same class, thus making the classification problem a little harder. So we are now going to take a look at the distribution of images provided for each class. It is evident that there is a non-uniform distribution of images per species. For example, there are almost 3 times as many images for one species in the training dataset as compared to another, which can lead to a huge bias during training. Also, there are a low number of training images overall, which may lead to overfitting on the dataset. Next, we also used principal component analysis to reduce the dimensionality of our dataset while still maintaining most of the key information present in the original set. Initially, the dataset had 6,075 dimensions. We then tried to reduce it to around 2 dimensions. The important concept here is that these dimensions should be the principal components and represent the key characteristics of the dataset. This is done by first selecting the dimension having the highest variance, and by then selecting another dimension having high variance, which is not correlated with the first. During our analysis, we found that when PCA was applied to the segmented image dataset, the components identified had a higher variance. Thus, we'll also use the segmented image dataset to test our models against later to see if model performance improves. We now move on to the data pre-processing steps, which involve image resizing and normalization, and trying out various techniques to balance the different classes. So in the normalization step, the pixel values were normalized to a range between 0 to 1. This was done to help faster convergence of gradient descent-based algorithms, such as neural networks, and also help make features contribute equally in distance-based algorithms, such as KNN and K-means. Images were also resized to specific sizes as required by the models being used, because machine learning models expect a fixed size training dataset of images. We now move on to trying to balance the dataset to handle the data imbalance perceived earlier. The first approach is by using GANs. GANs, or generative adversarial networks, work by producing artificial data samples from the original small image dataset. A GAN consists of 2 distinct models, a generator and a discriminator. The generator produces fake images capturing properties of the real images, while the discriminator identifies if the generated images are real or fake. Both models keep improving on the functionality during training, and equilibrium is achieved when the discriminator can no longer give a correct classification for the images outputted by the generator. We use 2 types of GANs in this approach. The first was a deep convolutional GAN, or the DC GAN. The DC GAN uses convolutional and convolutional transposed layers in the discriminator and generator respectively. The generated images from random classes, which was a problem because we want to target particular species which have less data in the original dataset. So even though the DC GAN generates real images, we could not use it to balance the dataset because images are generated from random classes, which may worsen the data imbalance. The second approach was the conditional GAN. The conditional GAN makes use of class labels in addition to the images as input, both to the generator and the discriminator models. However, the outputs of this model aren't that desirable because the generator is unable to capture many axes of variation that are present in the original images. This is most likely due to insufficient training instances for each class along with the skew in training data. We could improve on this functionality, but we were not able to do this during the duration of this project due to computational drawbacks. The second approach we tried to balance the dataset was image augmentation, in which we enhance the training set by creating transformed versions of existing images. This improves the performance and ability of the models to generalize. The techniques we used in this project were that we used random perspective transformation of the given image with a given probability. We also implemented random rotation, random affine transformation of the image, keeping the center invariant, and image flipping along both the vertical and horizontal axes. The last and final approach we tried was image segmentation, in which we enhanced the training set by partitioning images into different regions or segments under respective class labels. This helps by highlighting the segments that are better for the model to pick up while training. In the segmentation procedure, we first separated the background pixels from the foreground pixels, thus removing the noise from the images. This was done using the hue saturation value to create masks for plants to partition them on. We also sharpened the segmentation mask to get a better quality of images. To summarize, during this data pre-processing step, we created four types of data sets that we then used to evaluate our model performance. The four types are the original data set that was provided on Kaggle in the challenge, the segmented data set, which is basically the original data set with image segmentation implemented. Then we have the balanced data set, which is the original data set augmentation. And then we have the balanced segmented data set, that is the original data set with both segmentation and augmentation. The final data set had around 12,000 images in total, with 1,000 images per class.
Now, let us move on to the machine learning solutions that we implemented. First, we will talk about the two basic clustering models that we implemented, k-means and k-nearest neighbors. K-means is an unsupervised learning algorithm for clustering data. It classifies based on any data patterns that it finds in the trained data. We need to set the initial number of clusters for this algorithm, which is set to be k equal to 12, since we have 12 different classes. The best performance for this model is on the segmented dataset with a train accuracy of 30.99%. On the other hand, KNN is a supervised learning algorithm which assumes that similar training instances exist in close proximity. To tackle the multi-class problem, we use one versus rest classifier on the k-neighbors classifier. This helps us to split the multi-class classification problem into one binary classification problem per class. The best performance was observed on the segmented dataset again with a public score of 51.19%. Next, we tried to implement a custom convolutional neural network architecture and trained on it. CNN specializes in processing data that has a grid-like topology, such as an image. The basic CNN model of our structure is shown here. That is convolutional layer followed by batch norm, followed by leaky ReLU. Due to time constraints, we will now talk about the key highlights of our implementation. We use leaky ReLU here as it solves the problem of dying ReLU. It substitutes zero values with some very small values, say 0.001. Thus, the gradient descent will have a non-zero value, so our model will be able to learn without reaching an end. A softmax activation function for the last dense layer is used, which is necessary for a multi-class classification problem. Further, we chose to tune the beta 1, beta 2, and epsilon values for our optimizer atom so as to control its momentum. For this model, the best performance was on the segmented dataset with a public score of 96.725%.
Okay, so now I would like to I will be presenting about transfer learning. Firstly, what is the transfer learning? In simple terms, it is a machine learning technique where a model changes on one task in risk purpose on a second related task. And for our task here, we will apply pre-trained models for image classification tasks. The intuition behind it is that it allows us to learn complex feature maps from training model on large image dataset without having to start from scratch. It helps to achieve higher accuracy. And in this project, we experiment with 3 different pre-trained models: efficientness, inception ResNet, and exception. All 3 models were pre-trained on millions of images from ImageNet dataset before further training with our 4 datasets. And the validation size is 10% of the dataset size. And before jumping into the details, I would like to point out some general practice that we use for this approach. So firstly, we will unfreeze all the layers. Although it will increase the training time as more layers, we could achieve better results because they learn better features for the downstream tasks. Secondly, we also implemented some layer following the original model architecture, which has patch norm and dropout. And thirdly, we added some callback functions to improve the performance by adjusting learning rate during training. So they are early stopping and reduce learning rate on plateau. So early stopping was used to stop the training once the model stopped improving, and the second one is for reducing the learning rate if the loss increase over a period. Nice. So the first model we tried is efficientness. The efficientness family not only provides better accuracy but also improves the efficiency of the models by reducing the number of parameters as compared to other state-of-the-art models. And efficientness was on the idea of increasing model size by an effective compound scaling method, and which can help the model achieve maximum accuracy gains. And here we select a P3 variant, and it provides a good compromise between accuracy and computational resource. And from the training and test, the model gave best result on the original dataset with score of 0.98, and the hyperparameters are shown in the image. Okay, and so next model is in Inception ResNet V2, and it is a CNN model that builds on the Inception family but incorporate residual connections. So this type connection is a type of skip connections that learn the residual functions with reference to the layer input instead of learning unreferenced functions. And for this model, our dense layer use the miss activation functions instead of ReLU. So miss is a recent activate function which is unpowdered above and powdered below. So such attributes prevent model from saturations due to cutting, and and it allow better gradient flows than ReLU. So, and in this experiment, the model get pair result on parent dataset with score of 0.97 with the hyperparameter shown in the image. Okay, and the final experiment is exceptions. Basically, exception is an extension of the inception architecture, which replaces the standard exception models with the depth-wise separable convolutions. So here, the exception model challenges the concept that we need to consider both the space and depth at the same time. And for this model, our dense layer use the cell activations. So it is a self-normalization activations that allows the network to converge faster and avoid vanishing and exploding gradient problem. And here the model get pair result on the parent dataset segmented with score of 0.97 with the hyperparameter shown in the image.
Moving on to vision transformers. Moving on to vision transformers. A vision transformer is a model for image classification that employs a transformer-like architecture over patches of the image. An image is split into a fixed size patches, and each of them are linearly embedded, and then the positional embeddings are added. And finally, the resulting sequence of vectors is fed into a standard transformer encoder. To perform classification, the standard approach of adding an extra learnable classification token to the sequence is used. Recently, vision transformers have achieved highly competitive performance in benchmarks for several computer vision applications such as image classification, object detection, and semantic image segmentation, and that's why we chose to use a vision transformer for our project. So the table on the left shows the hyperparameter settings for a vision transformer. We also use dropouts and early stopping to prevent overfitting, and our vision transformer achieved an F1 score of 0.87027 on the leaderboard when trained on the original dataset. So while the vision transformer architecture is a promising option for vision processing tasks, the performance of vision transformers is still inferior to that of CNN alternatives such as ResNet when trained from scratch on a smaller mid-sized dataset like the Plant Seedling dataset. So we utilized a pre-trained transformer available from the Hugging Face library and fine-tuned it on the Plant Seedling Classification task by disregarding the multi-layer perceptron layer and adding a new classification layer. So the vision transform model was trained on the ImageNet 21K dataset, which consists of 12 million images from 21,843 classes. We used early stopping to stop training once the validation loss stops improving, and our vision transformer was able to achieve an F1 score of 0.98110 on the leaderboard when trained on the balanced dataset. So moving on to ensemble methods. Ensemble methods use multiple learning algorithms to obtain better predictive performance that could be obtained from any of the individual learning algorithms alone. So when we ensemble multiple algorithms, we need an aggregation method. For our project, the aggregation method that we used was a weighted average method where we take the weighted average of the probabilities of top performing models. So due to the low cardinality of the dataset, we avoid stacking and blending ensembles since they require a lot of data to train the base classifiers as well as the meta classifiers in order to prevent overfitting. So we experiment with the weighted average by weighting the average of the predictions of our exception model, our inception ResNet, as well as the EfficientNet B3 models. So the weighted average and ensemble results as shown on the table on the right. As you can see, it achieves a score of 0.99118 on the leaderboard, and all of the weighted average ensembles outperform the individual classifiers involved. So the equation of a final and weighted average ensemble is given below. So we also experimented with multiple other techniques, which we will be covering now. So test time augmentation, just like what the data augmentation does in the training set, the purpose of test time augmentation is to perform random modifications to the test images. Thus, instead of showing the regular clean images only once to the trained model, the model will see the augmented image several times, and the predictions of each of these corresponding images are then averaged out, and the final prediction is calculated from this average value. So we used 20 augmentation of the test image, and this was implemented with Kira's data generator and the PyTorch data loader. And from the table on the right, you can see we achieved a score of 0.98614 using the inception ResNet along with test time augmentation, and this corresponds to the top 4.8%. So from the confusion matrices seen before during the presentation, the convolution layers often misclassify black grass and loose silky bend. On reinspection of the data set, you can see that the images from these two classes are almost identical, and this is the reason why our models can't classify these images accurately. So to correct this error, we propose a binary classifier that changes the prediction of the main model if the prediction is a black grass or a loose silky bend. So a binary classifier is trained only on images from these two classes from the balanced data set. And our hypothesis is that the binary classifier will better distinguish these two classes than our main models and help improve the scores. We used an EfficientNet 3 along with batch normalization and dropouts, and the final classification layer is a one neuron layer with the sigmoid activation function for the binary classification task. However, as you can see from the confusion matrix, the binary classifier still misclassifies the black grass and loose silky bent images. And from the table on the right, you can see our models perform much better without the use of the binary classifier, and using this binary classifier only worsen the performance of our model on the leaderboard. So coming to our leaderboard, we were able to achieve a rank of 13 out of 833 teams, and this corresponds to the top 1.56%. And we were able to do this using the weighted average ensemble, as mentioned earlier. So for solution novelty, we studied and employed different activation functions such as the SELU and MISH in order to improve the performance of our model. Just using a pre-trained model doesn't achieve very high scores. We need dropouts and batch normalization to prevent overfitting. Callbacks were also used to prevent overfitting and help the model converge to the local minima by reducing the learning rate. We improved our score considerably by combining our best individual models by weighting their predictions. And lastly, we showed that vision transformers can achieve very high scores in the competition, and vision transformers have not been used in the competition before. So to conclude, exploratory data analysis is very important since we can understand the data better and come up with good and creative solutions. Convolution layers are the go-to for vision tasks, and transfer learning is very useful and it helps improve our scores when the data set is very small. Batch normalization, dropouts, and callbacks help to prevent overfitting and help the model converge to the local minima. And ensembling helps us improve our scores by a significant amount, as we showed earlier. And lastly, we realize that creative thinking and good teamwork is very essential to achieve high ranks in casual competitions. So that brings us to the end of our presentation. Thank you so much.